Hello everyone, it's my pleasure to share my CVPR paper. This work is proposed for the Class-Incremental Semantic Segmentation task to address the problems in the existing same-based methods, including the local view and the inefficiency as the learning tasks increase, and the problem that existing knowledge distillation method limits the model's plasticity. We propose a new transformer-based framework dubbed Incrementer, which is a new structural paradigm with both high performance and high efficiency. We also propose a novel knowledge distillation method that only distills the features corresponding to the old class regions and improves both the stability and plasticity of the model. And we further propose the class deconfusion strategy, which is used to balance the learning of the old and new classes. Next, we will introduce our method in details. We'll first introduce the transformer framework, which consists of an encoder and a decoder. For the encoder, we adopt a vision transformer to extract visual features and capture more global contextual information based on the self-attention mechanism. For the decoder, we assign a class token to each class and then put the class tokens into the transformer decoder jointly with the visual features, and generate corresponding visual embeddings and class embeddings. Finally, the segmentation mask of each class is obtained by calculating the similarity between each class embedding and the visual embeddings. Based on the above transformer framework, in incremental learning, our method only needs to add new class tokens to the transformer decoder to predict new classes, and the old and new classes can be predicted in parallel, which is more efficient. We further adopt the pseudo-labeling strategy to alleviate catastrophic forgetting and the problem of background semantic shift. We first generate the pseudo-labels of the old classes through the old model, and then we combine the pseudo-labels with the ground truth to train the current model. Existing knowledge distillation methods treat the feature map as a whole and neglect to distinguish the regions corresponding to the old and new classes, while in semantic segmentation, different classes corresponding to different regions, and the old model lacks the ability to recognize the new classes and regards the new classes as the background. If all features are distilled by the old model, it will be difficult for the current model to generate more discriminative feature representations for the new classes, thus limiting the plasticity of the model. Therefore, we argue that not all features in current model must be distilled by the old model, and we propose a novel knowledge distillation scheme, FOD, that only focuses on distilling the features of the old classes. We first perform FOD on visual embedding features. We get the old class regions through the current ground truth, and perform knowledge distillation only on the features in the old class regions, as the features with blue borders. The knowledge distillation laws utilize the cosine similarity. The visual embeddings represent the visual features of local patch, so the distillation on visual embeddings is the local level distillation, while class embeddings capture the global information of each class through the transformer decoder. Thus, we further perform knowledge distillation focused on the old class embeddings, as the features in the red dashed box, with the above distillation method at the local and global levels. We improve both the stability and the plasticity of the model. In the process of incremental learning, we observe that when the new data contains a small number of samples or new classes, it will cause a small number of new classes with high probability of occurrence and a high concentration, while a large number of old classes have a low probability of occurrence and are scattered. The imbalance between the old and new classes causes the model to overfit the new classes and result in false positives. Moreover, if the new data contains similar classes to the old classes, the model will confuse them. So we propose a class deconfusion strategy, CDS, for this problem. First, when training on data with only a small number of new classes, the new classes occupy a large proportion of the segmentation loss, which reduces the network's attention to the old classes. Thus, we reduce the weight of the new classes in the segmentation loss to alleviate overfitting. Second, to solve the confusion of the similar new and old classes. Therefore, we propose to classify all the old classes into one class to improve the concentration of the old classes, and generate a no-new binary mask. We use dice loss to solve the imbalance of the binary segmentation. We first perform experiments on Pascal VOC. Our method significantly outperforms the previous state-of-the-art methods by a large margin on all 4 protocols, about 6 to 15 absolute points on all MLU. And the superiority of our method is more obvious in the long-step learning. We further perform experiments on the more challenging AD20000 dataset. In the short-step learning, our method outperforms existing methods on all MLU by more than 9 absolute points. In the long-step setting, our method outperforms existing methods by 5 and 20 points. To verify the effectiveness of our proposed FOD and CDS, we perform ablation experiments on Pascal VOC. FOD improves the method's performance on new classes by over 15 points, and CDS further improves the performance of our method on new classes by nearly 20 points. In the setting of long step with few new classes, we calculate the proportion of false positives MFP in the old and new classes, as shown on the right side of the table. Higher MFP means that the model overfits the new classes. Our CDS not only reduces the overfitting of the new classes, but also improves the discrimination of similar classes, such as shape and call, tree and bus, thus obtaining better overall performance. The figure shows the visualized segmentation results. For some classes that are easy to be confused, such as bus, shape, our method can distinguish confusing classes without forgetting the old classes and generate more accurate segmentation results. Thank you very much for listening to my presentation. Thank you.